Thanks for having me. It's a real honor to be here. Excited about the turnout, and I'm excited to talk to you about climate change in Arizona, look at the past, present, and future. And I'll just give you a little bit of an overview about the way I want to try to present this information today. And I usually don't jump right into the main issue right here. I think it's really important, since we're really concerned about water resources, we're concerned about climate in Arizona, we're concerned about resource management, is that we have a little bit of background on the climatic context for the area, okay? And we all know, I think we know, what the climatic context is. It gets hot here in the summer, it's cool in the winter, sometimes it rains every couple years, those kinds of things. But I think it's good to actually look at some of the data, because human beings are terrible, terrible climate recorders. We're not very good at it, all right? And I stare at climate data all the time, and I will invariably wrong on when I say, this is the hottest day it's ever been, or, oh, it hasn't rained in 40 days or something like that, right? So going back to the data is really that most critical element of providing that climatic context. Then we'll move into this idea of the fundamental issue at hand of the greenhouse effect and its influence, or its driving force, the fundamental driving force in global climate change. And then I'm going to just continue to try to drill down in the synthesis information that's out there, thousands of scientists working on this, of why we think that there's something going on, what are the fundamental basic physics behind some of these changes, go into observational data. Again, this is an issue of there's no one particular argument that is definitive. It's a weight of evidence issue. We have to use all of this information together to look at the particular issue, and we're using this in a risk management context, right? This isn't about anybody being definitively right. It's about using a lot of information in the best way that we can. So I'm going to use observational information. We're going to look into the past. We're going to look at time series data. We're going to look at maps. We're going to look at these different types of things. And then finally, we'll get into that dark art of scenarios and projections, trying to predict the future, right? And so I have a real issue with this as well. I think trying to predict the future is a really, really difficult part of it. Again, this information in my mind is really about risk management. It's about inputs and outputs and making decisions with the information at hand. We can use these scenarios to try to understand risk management, but we really can't predict the future definitively, right? So people always want me to tell them if it's going to rain next week on this day. They also now want questions like, in 50 years, what will the climate be like, right? We can put guardrails on this information by looking at projections, but again, that's not what this is about. It's about predicting the future definitively. It's about making choices and with this information. And then really drilling down to potential implications for Arizona. Okay, so this climatic context may seem a little boring, but I hope that this is kind of one of the more important parts of the presentation, is that we just step back and look at Arizona climate, all right? And you may not be able to look at it in the way that I'm able to look at some of this data, so I'm going to try to present it today, and I may have a laser pointer on here. This actually could turn off the air conditioning in the building, so, okay, it didn't. Okay, good. So just to orient you to these two maps here, these are maps of gridded estimates across the whole state. So we're taking point observations, long-term observations of temperature and precipitation. And knowing that temperature decreases with height, we can then make statistical estimates of what it's like between stations. So we can make maps of surfaces, right? So this is a map of temperature, annual average, long-term average, at least 30 years of temperature across Arizona. And these are watershed boundaries superimposed on here. And the reason I like to show this is that most of us aren't from Arizona. Is that correct? Am I correct in saying that? There's very few of us are from, and a lot of us are from places back east that are flat, okay? So weather and climate is much simpler in places that are flat, okay? And when places have elevation and lots of topographic relief, the climate gets complicated, all right? And this map is to show that complication, is that we know this intuitively. Upper elevation locations are cool, lower elevation locations are warm. But if you look, we have gradients over very, very short distances that have fundamentally different climates. And you know that, right? As you drive anywhere in Arizona, the vegetation changes. It can change very abruptly as you go uphill, right? Okay, so that's getting you thinking that the climate just spatially is very complicated across Arizona with one of the more simple metrics, which is just temperature, which organizes itself spatially pretty easily. Then we get things like precipitation, and you notice here that this map has temperatures that would be the equivalent climates of middle Canada, all right, and then places in Arizona that are as warm as some of the lower valleys of California, okay? So we have in one state, and sometimes in one watershed, climates that you would need to look on flat areas, many tens of degrees of latitude across the planet, all right, in small locations just like Arizona. Okay, that's just temperature. If we go to precipitation, it gets even more complicated because in general, precipitation does follow a relationship with elevation, but not always, all right? We have this nice band of wet conditions that are normally seen on the highest elevations of Arizona. You can see some of the peaks of the Sky Islands here across Arizona. We also have high cool deserts that are produced by a rain shadow. So when moisture comes in off the Pacific in the wintertime, it gets pushed up over the Mogollon Rim, it gets wrung out, and then you have a drying signal on the Colorado Plateau here. We have some of these valleys filling in with precipitation that you wouldn't normally see at that elevation because monsoon storms can move off the mountains and dump rain in the valley. So you get this really interesting sort of patchwork. And again, looking within watersheds, you have very, very steep gradients in precipitation, right? So we try to think of these blocks of either watershed units or land management units or counties, and it's hard to say what the climate of that place is because you can move a block down the road and it can be a little bit different, all right? So that's that challenge that, when we wrestle with climate in its current incarnation and in its past, and when we think about it in the future, is that this context is really critical, is that will it change the same everywhere in every part of the county? Maybe, maybe not, right? And that's where the science has really, really shoved to the wall, is that predicting at that scale, we're just not able to do, okay? So we have to think of strategies that don't put us in very vulnerable situations based on having a really complex climate. Okay, so some things then to think about that spatial organization of climate. Now we turn towards another fundamentally unique part of Arizona climate, which is its seasonality. We live in a seasonal transitional climate. Again, you know this stuff, but again, I'm just trying to put some data to it and a little bit of context spatially and temporally, is that these little bars right here represent the long-term annual average monthly precipitation for different what we call climate divisions, and they're you can see here that it's a really fancy term for counties clumped together. Here's Yavapai gets its own climate division. You should feel very, very lucky there. Look at poor Northeast Arizona. It's got a share 3 counties here. But we do this because we don't have a lot of stations in Arizona, right? We have to, and this is across the western U.S. We don't have a lot of stations. So we have to lump large land areas together to come up with a mean climate signal, the average climate signal over large areas. We know we miss a lot in the in-between, but again, this is just a large-scale pattern here. And the point of this graphic, again, is that these little bars represent the annual cycle of precipitation in Arizona, okay? And you know this, but if you're not from here, or you're somebody back east looking to the west, thinking about climate variability, this is nuanced. All right, and the nuance here is that we have one, and I'm using air quotes here, wet season in the wintertime and one wet season in the summertime, right? With intervening dry periods, as we just have come through, or kind of still in April, May, and June. And then the fall is a really interesting toss-up season that has huge variability if you look at the long-term record. Most of the time it doesn't rain at all in October, but every once in a while you get 12 inches out of a tropical storm. That's climate in Arizona right there, high variability. But this idea that we have one winter wet season and one summer wet season with intervening dry periods means that we transition from wet period to dry period to wet period normally every year, and the mechanisms that produce the precipitation in each of these seasons is different. All right, and again, you know this. When in the wintertime, the storm systems are out of the west and the northwest. They're usually cold, and they'll sometimes produce snow. So they're actually part of the weather that the rest of the United States experiences. The jet stream activity, those snowstorms you're trying to make connections through O'Hare, that's the kind of weather systems that's impacting Arizona in the wintertime. The dry season, it gets windy, the jet stream lifts to the north, and then we move into the North American monsoon season, where we have a shift in wind and we actually start to pull subtropical moisture from the equator north. So think about that. We have, in the whole context of the northern hemisphere, we're geographically at a tipping point based on weather systems. In the wintertime, we're sharing weather with the rest of the northern hemisphere all the way to the poles. And then when we get in the summertime, we flip around and we start participating in tropical activity. That's amazing. That's really amazing. You can't find too many places in the world that have two fundamentally unique seasons back to back through time that have their own independent modes of variability, meaning they can kind of do this away from each other, they can sync with each other, and then produce droughts that occur both seasons, or intermediate or wet seasons that occur both seasons, but are pretty much unrelated through time. That again complicates how water gets moved into Arizona. So that's just the big picture here. But look at these graphs as you carve Arizona up here. Hopefully you notice a couple things about the winter versus summer signal. As you go this way across the state, you may notice that the bars in the summer get taller and taller and taller. That's not an optical illusion there. That is indeed the case, is that the southern part of the state is closer to that subtropical moisture. The monsoon system is primarily, if you don't know this, that Mexico gets almost 100% of its total precipitation in the summertime, right? They very, very rarely get winter storms move that far south, okay? So then so as you get further and further south, you get more of a summer signal. As you go further and further north, you get more of a winter signal, right? Because we're closer to the weather that's impacting the Rockies, the Pacific Northwest, right? So even in a state, you have a slight differential in the seasonality of precip. Cochise County gets on average about 65% of their annual rainfall comes during the summertime. Kind of interesting, right? As you go into Yavapai County, it's almost equal. It's almost 50-50. And as you go further north away from the monsoon, it gets tipped even more, right? So as you move, there's a gradient across the state and across watersheds. All right, and again, any given year, that signal can be totally washed away because the variability of that given year drives what happens in that year. This is the climatological signal we're trying to look at, okay? And then another nuanced part of Arizona climate is this idea of aridity, or and it's driven by this idea of potential evapotranspiration, $10 word, that simply is, as you know what evaporation is, it's the combined effect of evaporation and transpiration, which is the use of water by plants. Okay, so as plants are drawing it up and using it out of their leaves, this combined effect gives us an indication of what that draw on soil moisture is in a particular location. Okay, and these are hard to read, but I'll just orient you to that this low elevation area here is a potential evapotranspiration amount of 50 inches a year. Okay, meaning a depth of 50 inches of water a year would be used up in potential evapotranspiration. Okay, so that's what the climate is hungry for. That's what the atmosphere is hungry for, based on being very, very hot and very, very dry. The atmosphere wants to put that into the atmosphere. The atmosphere wants to put that water into the atmosphere. Okay, and then at higher elevations, we go down to potential evapotranspiration amounts of 20 inches. Okay, and so just to cut to the punchline here, these upper elevation areas of about 20 inches of potential evapotranspiration get on average, about 40 inches of precipitation. Again, these numbers are, you're probably thinking, when, right? When did that place get 40? On average, the wettest and the driest average together. So 40 inches coming in, 20 inches being taken out by potential evapotranspiration at the highest, coolest parts of the state means that there's 20 inches of water left over on average, okay? That, when you have that situation, that we call that surplus in a water balance, surplus turns into base flow in streams, right? So there's no mistake that that's where you're getting actual water being generated that can actually move in a surplus situation. Again, interannually, that situation doesn't happen every year, right? We have strings of droughts, we have strings of wet periods. I'll show you a little bit of that, but this is the context. The source areas of water in the state are clearly the highest, coolest elevation parts. But just to give you a feel for the gradients here, as we get down in elevation here, these potential evapotranspiration amounts go up to 40 inches and up to 50, and they're actually even quite higher than that based on current climate data, that these areas on average are getting maybe 10 inches on average of precip coming in. 10 inches coming into the water balance, 40 being desired by the atmosphere. That is a deficit. That's an arid climate, okay? And these gradients are occurring over very short distances, right? So look at Yavapai, a very complex climate of high evapotranspiration, low precipitation at lower elevations, and then maybe a wash, probably not, still a deficit at upper elevations. Again, that's why you're having episodic runoff events, because climatologically, the climate is just not tuned up to generate. This is not Washington. That was the punchline to this whole slide. This is not Washington State, right? Is that we do not live in a wet climate, right? I think we forget that sometimes, right? A wet month here or there, and as I'll show you with some of these slides, those of us, and it wasn't me, that have moved here since the 80s, or we put policies in place, we have had very, very wet periods in Arizona, recent Arizona history that are completely out of bounds of what we'd expect in the historical record.